In graph theory, we say that a graph G with vertex set V and edge set E is a bipartite graph if the vertex set V can be partitioned into two subsets, let's call them A and B, such that every edge in the edge set E has one endpoint in A and the other endpoint in B. Further, a graph G is a complete bipartite graph if every vertex in A is connected to every vertex in B. Alright, I've created two graphs down here that I'm going to use to illustrate the difference between a bipartite graph and a complete bipartite graph. So let's consider this first graph right here with 5 vertices I've labeled A, B, C, D, and E. To determine if this graph is a bipartite graph, the easiest way to do that is to check if it is two colorable. And what that means is, are we able to color all of the vertices in this graph using only two colors in which no two adjacent vertices have the same color? So to do this, let's first pick any vertex that we want in the graph. So let's pick vertex A and let's color it using any color we want. So let's say green. So we can see that vertex A is touching or is adjacent to vertex D and vertex E. So both D and E need to be colored using a different color. For this example, I'll just choose red. Now we just continue this process with every vertex. So if we consider vertex D, it's adjacent to vertex A and vertex C. So both A and C need to be different colors than D. So we can see that A is already green, so we need to color C green as well so that it's not matching this red color of D. So we'll go ahead and color C using a green color. Alright, and then if we move on to vertex E right here, for every vertex that E is adjacent to, it also needs to be a different color. So we can see that E is adjacent to A and B. So both A and B need to be a different color than E. So A is already green, so that's good. Now let's color B green as well. Now if we consider vertex B, it is only adjacent to vertex E. So it just means that B and E need to have different colors, which they do. And then lastly, if we consider vertex C, every vertex that C touches, in this case it's only one vertex, it needs to be a different color, which we can see C and D are different colors. So because we were able to color the vertices of this graph in this way, such that no two adjacent vertices have the same color, it means that this is a bipartite graph. And if we consider the original vertex set V of this graph, we are able to partition this vertex set into two subsets based on the colors in this graph. So we could say that subset A is, let's call it the green vertices, so A, B, and C. And then we can make another subset B, let's call it the red vertices, so D and E. When we partition the original vertex set into these two subsets, A and B, we'll find that every edge in the original graph has one endpoint in A, let's go ahead and circle those, and one endpoint in the subset B. So if we consider, for example, this edge right here, we can see it has one endpoint in subset A and one endpoint in subset B. And if we consider this edge right here, we can see it also has one endpoint in subset A and one endpoint in subset B. And we'll find that to be the case for every edge in this graph. So that's the definition of a bipartite graph. Now, in order for a graph to be a complete bipartite graph, it means that every vertex in A needs to be connected to every vertex in B. So if we consider our subset A right here, is every vertex in this subset connected to every vertex in this other subset B? Well, we can see that, for example, vertex B is not connected to vertex D. And we can also see vertex C is not connected to vertex E. So although this is a bipartite graph, it is not a complete bipartite graph because every vertex in this subset A is not connected to every vertex in this subset B. But if we jump on over to this graph right here, we'll find that we're able to color the vertices in the exact same way. Or in other words, we're able to partition the vertex set into these exact same two subsets. But for this graph, we'll find that it is a complete bipartite graph because every vertex in subset A is connected to every vertex in subset B. So we would call this graph a complete bipartite graph compared to this graph, which is just a bipartite graph. Now, when we have a complete bipartite graph like this, we label it as K, so capital K, sub M, comma N, where M is the number of vertices in the first subset. So in this case, this first subset has 3 vertices. We would write K sub 3, and N is the number of vertices in the second subset, which in this case has 2 vertices. And one cool property about a complete bipartite graph is that the total number of edges will be equal to m times n. So in this case, that would be 3 times 2, which is 6. So this is actually a quick way to verify whether a bipartite graph is a complete bipartite graph or not. So in this case, we can verify that this graph does have 6 total edges if we count the total number of edges. But in this graph, we'll find that there are only 1, 2, 3, 4 total edges. So that's how we know it's not a complete bipartite graph. So just keep that in mind.